Okay, so we're looking at arithmetic series. We've already looked at what we mean by an arithmetic sequence. So what do we mean by series in general and arithmetic in particular? Well, as soon as we add the terms of a series, a sequence together, we have a series. So this has got, this here is an arithmetic series. Okay, we're just, as soon as we see the add there, that's what makes it a series. We're just adding together the terms of an arithmetic sequence together. Okay, so we can write lots of these. 100 plus 95 plus 90 plus 85 ... That's an arithmetic series. The add is what we're looking for when we're talking about series. There's got the terms will be following a particular rule, in this case arithmetic, and the series is the add between the two. That's the thing that makes them a series. Okay, so we're going to introduce you to some notation here. Sn means sum to n terms. A, as we've seen, is the first term, and n is the number of terms, and D is the common difference. Okay, and un, as we've seen before, is the nth term. And we've already seen a formula for un, which is a plus n minus 1 d. Okay, so when we're looking at adding the terms together, more generally, we've got a is the first term. The second term is the same as the first term, but d more. And the third term is the same as this term here, it's the second term, but with a further d, and so on, until we get to our nth term, which is a plus n minus 1 d. Okay, and what we're going to show today is that there's a formula, rather than adding them all together, which is actually in the formula book, which goes like this. And we're going to prove this well-known result, which is in the formula book, for the sum of a series. Okay, well, before we do that, we're going to actually make it a bit simple first of all. Apparently, there's a famous mathematician called Gauss, who was once asked, as a very young boy, 9 years old or something like, in school, to add the first 100 numbers together. What might seem quite time consuming, but apparently this lad, child prodigy that he was, came up with the answer very quickly. So how did he do this? Well, it was probably something like this. He would have reversed the numbers, write out the same series but backwards. Of course the sum here would be exactly the same, it's the same series but working backwards, and then of course the last term would be 1. Okay, now if you add these terms together, you'll see that each one of them is 101. But of course we'd have to add these two together as well. So 2 times S100 equals to 101 plus 101 plus 101 plus 101, so on all the way to the last term, which is also 101. Of course we've doubled our sequence because we've added the same thing together. How many terms are there? You should see that there's 100, because there's only going to be the same number of terms that there was before. And we've got the numbers 1 to 100 here, so there must be 100 terms. So we've got 100 lots of 101, so that comes to 100 times 101 which is 10100, not difficult. And we can divide those by 2. So that's 5050. Not bad for someone 9 years old. There we go. Right, we're going to actually do something a little bit similar. But say, remember, we're heading towards proving this. Okay, we're heading to something similar, and that is, but not exactly the same, a little bit less general. Imagine we had the same sequence of numbers, but we don't know how many there are. So it's the same series up to n. Right, let's do the same thing. Write backwards and add. Obviously the last term would be 1. As we added these together, we'll see that all of the terms come to n plus 1. Every single one of those. So we would have 2Sn is equal to n plus 1 plus n plus 1 plus n plus 1, so on. And how many terms are there? Well, there were n terms here, so there's going to have to be n terms here. So we've got n lots of n plus 1. So 2Sn is equal to n plus 1. So Sn is equal to n bracket n plus 1 over 2. Okay, so there we go. That's the formula, a well-known formula actually, for the sum of the counting numbers, or the sum of natural numbers up to n. Okay, well, this is a special case of the even more general thing, as I keep saying, is this. We're going to prove now. Okay, this is the most general, so this is the proof. Okay, so this is the proof of Sn equals to n over 2, 2a plus n minus 1 d. As I said at the beginning, if we call a the first term, and the common difference d, and the second term will be a plus d, and the third term will be a plus 2d, and the fourth term will be a plus 3d, and so on up to the last term, or the nth term, which will be a plus n minus 1 d. Right, well, let's just employ the same idea, write it backwards. A plus n minus 1 d. So we're going to couple these two together and add. Okay, then plus, now notice the term before here would be a plus n minus 2 d. Okay, so that's going these two together. Might be worth making a big add sign between these two to make it clear that those two terms are added together. And this, let's do one more term. That would be a plus n minus 3 d. Up until, again, the last term here would be a. Now, we can see that the same thing's going to happen. If we add all the terms together, they're all going to come to the same thing. Convince yourself if you want, but the first two are obvious. The first and the last, should I say, should be obvious that we can see, because we're adding a here to this here, and all we're going to get there is 2a, because it's just a onto that. Okay. Now, again, let's maybe separate these out to make it clear. So these two added together. Well, it will also be, and we may want to convince ourselves, but it will also be a plus n minus 1 d. Up until those two. And they're all going to be the same thing. So we check. Let's see if we can check. Let's just check for these two, just in case. But it's the same pattern going on. I'm certainly not going to check them all, but just to show you the idea, we've got a plus d added to a plus n minus 2 d. Multiplying that all out, we get a plus d plus a plus nd minus 2d. If we remove the bracket, we get a plus d plus a plus nd minus 2d. Now the 2d's can be brought together. So we've got 2a, and the a's can be brought together, plus nd minus d. If we factorise that, that's 2a. That's quite a long-winded way of showing that let's write the d in the same way as well, n minus 1d, that this particular one here would add to the same, and all of them will add to this same amount here. Okay, let's rub all that out, because it's not necessary when it comes to showing it. Each one of these terms will come to 2a plus n minus 1d. How many will there be? Well, just like it was in the last example, there'll be n terms. So we have, oh, I should have put 2 here, just as we were adding the 2 together. So we have 2Sn is equal to n bracket 2a plus n minus 1 d, which is Sn is equal to n over 2 which was the thing that we were asked to, that I said we were going to show, and we've done it. That's the proof of the sum to n terms of an arithmetic series. Okay.